So go ahead, right on the top of this, do Thursday. And on the top, I'm also just going to briefly, like 1 minute, talk about those video notes. That's the whole reason I had you watch them, is so we could just do homework today. So at the top of this, I want you to make sure you have the guts of the exponential growth model down. Then we'll go practice it in the homework, so we're not doing a ton of examples. So the exponential growth model is triggered by when it says the rate of change, which is a derivative. So we're going to write on the top, I'm waiting for my marker to, man. Oh, there we go. I'm going to get the spinning wheel, but it should go. So go ahead and write on the top dy dt. At the very top up there. There we go. We'll write dy dt. Y is some quantity, and it's something that's growing or shrinking over time. So I'm just going to call it dy dt. You know you're doing exponential growth when they say it's directly proportional to the amount there at any given time. What that means is the more bacteria there is, the faster it will grow. That makes sense, doesn't it? So that's what that says. It has to be directly proportional to the amount there. If that's true, then if you were to separate, integrate, and all that stuff, you'll always get the same model. And in the video notes, I said it's y equals, and we kind of think of the word sect. But then I also in the video notes said to replace c with what? Y sub 0. Yeah, that's the initial condition. You can only do that if you have this exponential growth model. This is the amount present at time 0, which has to be handed to you. So that's our model. We're going to go practice it together on the puppy problem number 4. Then I'll pause the video and have you guys go do number 5. So we'll just go through, we haven't done one yet in full. We'll go do it right now. It says a puppy weighs 2 pounds at birth. That's my initial condition. That's my 0.0 time would yield 2 pounds. And 3.5 pounds 2 months later. So I'm going out in time 2 months, and I'm now up to 3.5 pounds. If the weight of the puppy during the first 6 months is increasing at a rate proportional to its weight, this is an exponential growth model. If I were to write the differential equation for it, a rate is a derivative. I need a variable for the puppy's weight. I would call it something that goes with the problem, either capital P for puppy or capital W for weight or something. Don't call it Y. Make sure you just make it go with the problem. Let's go, the rate of the weight change over time is directly proportional to the weight of the puppy for the first 6 months. There it is. Next step, because this is exponential, I'm not going to separate, integrate. The same thing happens all the time. I can just plop down a model for the weight of the puppy. Go ahead and do that. So what would you write down? You could integrate, separate, all that good stuff, but you don't need to. If it's pure exponential growth, what did you guys write? Equals what? C, e to the kt. But c is really the amount at time 0. So these have the same algorithm all the time. You can set up the diffie-q. You can immediately go to the solution. The solution to a differential equation is what's the weight. So the initial condition is W sub 0. That has to be handed to you unless you're told something else, and we'll get to that one later. So this said at time 0, the puppy weighed 2 pounds. So we're going to go like that. When you put in a 0, a 2 has to come out. So that means W sub 0 is 2. So there's that. Then we use the other point to find K. So we say, well, 2 months later, the weight was 3.5. So I replace W with a 3.5, and I say that's 2e to the, and I replace that with a 2, and I say 2K. That gets solved for K. So you need calculators for these all the time. So on your calculator, what will you do first? What are you going to do on a calculator? Yep, you're going to divide. So you'd go 3.5 divided by 2. What will you have to do with that? I'm trying to have you anticipate kind of the solving. You get rid of the 2. Then you'll natural log to undo the e. So you're going to have ln 3.5 over 2. And then you'll be dividing that by 2. So again, we divide by 2. We'd natural log. and then we divide by 2. You might even want to just do it like that. There it is, like just cancel them off. I just need you guys to tell me what that is. Because it's multiple choice, we'll round to 3 decimal places. If it pops up FRQ-ish, we would probably want to store that. Anyone want to give me a K? Do we have a 0.798? 2798, I mean? Does that sound right? Okay, so K is 0.2798. Sometimes they only ask for K. So 0.2798 is my K. That will go right back into my solution. Here's my solution right here. So my weight at any given time, I can find by doing 2e to the K, 0.2798 times time. So the question was, how much will the puppy weigh at 3 months? So you just plug in a 3 for T in your model and go to your calculator. And if you guys will steal it looks like Alexis has a B. Can anyone back that up? Yep, Riley. Okay, so the answer to that is B. I'm going to pause the video and you guys are going to go do number 5. If you're doing this with the video because you were absent, the answer should be C, but I'm going to pause. On number 6, there's going to be a little bit of a twist. I'm looking for my page turner. I don't see it. Do you guys see my page turner up there? Must be farther down. There it is. All right, so let's go look at number 6. 6 is that kind I said in the notes. It was one of the questions for the quiz. They always have to give you the starting amount and chart the rate and give you another point unless they tell you that things are doubling, tripling, or half-life of some sort. So let's go do number 6 together. It says a population grows according to that differential equation. It means Y represents the population at any given time. And it says to find the value of K. So I get to stop when I know K. It doesn't tell me where I started. It just tells me that it doubles. So again, this is about the population. So I have to write Y equals C e to the KT, which is Y sub 0 e to the KT. The reason they don't have to tell you the starting amount is because if it doubles, then this becomes 2Y sub 0. And these just cancel. If it tripled, it'd be 3. You can make a fake number and put it in. You could say, oh, it's doubling. You could have it maybe start at 10. It would grow to 20, and you do 20 divided. You'd still get a 2 there. Are we okay with that? So then now I just need to figure out what K is. Well, this was doubling, right, in how many years? 10. So now you just need to unwrap that for K on your calculator. Riley, what would you do on your calculator when I say unwrap that for K? Yeah, exactly. Natural log of 2 and then divide by 10. Yeah, natural logging will kill the E, so we'll do natural log, and dividing by 10 will kill the K. Whoops. We'll kill the K. And can somebody share what the answer is? I'm not going to run. A. All right. So now we're really going to put a twist to it. All right. So we're going to go into the one on the bears, which is number 9. You have to be careful when it's not exponential growth in your face, like when it's not the sect model. And so when we read through number 9, it says the rate of change. Well, this is dn. Let's go ahead and write that. dn dt, the rate that the number of bears is proportional, and it says directly proportional too. So I've got that word trigger, but it doesn't say to the right thing. If it was going to launch into the sect model, it would have had to have said directly proportional to what? N. Exactly. And it doesn't say to N. What does it say? 350 minus N. What that means is you have to do it. There's no shortcuts we can take for that. We can't just write N equals sect and C is the initial condition. We can't do that. We have to separate, which we know how to do. I just want to make sure you don't think every question is going to be pure exponential growth. So this is 1 over 350 minus N dN. Is equal to K, and my dt would whip over. Remember, K is a constant, so we like to leave constants over there on the right-hand side. What do we do after we separate? It's a good review of our last chapter. We integrate. Be very careful with the antiderivative on the left-hand side. K is a constant. It can come out front if you want to do it like that. But this is natural log, right, of 350 minus N. Why am I going to say be very careful? I'm going to actually write down, this is KT plus C like it's always been. Right here, if this was an FRQ and you took it on out to the end, you'd get 4 out of the 6 points, assuming you did everything else right. Can you tell me why? It should be a negative. Yeah, remember we can pass off to natural log when we end up with 1 over u du or u prime over u. U prime on this one isn't 1 though. What is it? -1. Yeah, so be very careful that you do that. What that's going to do is I need to get rid of it before I can exponentiate. I need naked natural log. So what I do is I take the opposite of both of them and I end up with natural log of 350 minus n is equal to negative kt plus c. So I have to do that. What would I do next, Eldridge? Yes, you're going to exponentiate both sides. So when I do it on the left, it'll undo the natural log. When I do it on the right, I get e to the negative kt plus c, which is times e to the c, right? So I still do get sort of that sectish thing, but it isn't like those other ones. All right, so right from here, I need to figure out, it says I need to figure out the bear population. So I am trying to figure out what n is. I would add it on to the right, and then I'd subtract the c e to the negative kt. It's now ready for you to figure out c. What do you think I'm going to use to help me figure out the c? Same thing I did in the other ones, right? It comes from the initial condition. It isn't the initial condition. So do you get the difference, Golden? So I am going to use 0, 100 to help me find the c. But if this was pure exponential growth, 100 is the c. So we just have to go and put in a 0 for t and make sure that 100 comes out. So I need 100 to equal 350 minus c times 1. So can you just see what the c is? What's c going to have to be, guys? Go ahead and tell me. What's c got to be? It's not 100. If I put in 100, this will poop out 250. So what does it have to be? 250, yep. E to the negative kt. So I use it, the flow of it's kind of similar, but you have to be careful that you don't think it's the same as those other kind. And I'll still use my other point. 2 months later, we're up to 250, right? So I still need to use that to find the k. So I still have to go here, and I'm going to have you guys help me on the calculator. I get 250, has to come out for my number of bears when t is 2, which would give me negative k times 2 or negative 2k. I need you guys to go solve that for k for me on your calculator. Make sure you do it correctly. 250 minus 350, divide by, I forgot the e on mine. I forgot my e. There we go. So 250 minus 350 looks like I get a negative 100. Then divide by negative 250. So I'm seeing 10 25ths. I could probably reduce that even more. Equals e to the negative 2k. Eli, do you get where I got that 10 25ths from? I subtracted 350 and got a negative 100. And I have the negative 250, so I actually just did 100 divided by 250. I took a 0 off. I could actually still even, I could call it 2/5. It doesn't matter because we're going to go to our calculator. So what do you do next, Mr. Dumas, for this one? Whoops, I just said that into the thing. So no one will know who I'm calling on unless everybody knows you're Mr. Dumas. How do I solve that for k? Yeah, so I'd natural log 10 25ths, and then that'll kill off the e, right? So I go ln, and then I would divide by negative 2, and I'd be left with my k. Can somebody tell me what that is, because we need it? Can someone back that? Thank you, 0.458. So k is approximately 0.458. Honestly, if it's not multiple choice again, I would store that, because if you round it and then use it again and round, if you're more than 1,000th off, it comes off an answer point. So you want to keep it as exact as possible if it's not multiple choice. Now it says find the bear population in 3 years. Well, I have my model. My bear population right here is equal to 350 minus 250 e to the negative k times t. Button 3, years, I'd put in a 3. So somebody run that through your calculator and tell me how many bears we have. Do you have it already, Bryce, or are you typing? All right. Those of you fast on your calculator, let's round to the nearest bear. Can I get a backer on that? 287? 280, awesome, thank you guys. So 287, we'll just finish this problem off. We'll go do part C. So this says find the limit as t goes to infinity for the number of bears. Really what this is, in Calc 2, you're going to learn that this is called the carrying capacity. It's the most bears that whatever habitat they're in can support. Does that make sense? But you just are going to run t to infinity on your model. Here's your model. Your n of t is equal to 350 minus 250, and then it's e to the negative, so I'm going to put it down here so you can see it better, 0.458t. Pretend t is going to a gazillion, times a gazillion, to the gazillionth power. That's what this is when I say I'm going to take the limit as t approaches infinity, limit as t approaches infinity. What happens to this whole chunk of stuff? When e gets as huge of a number, it gets so small that its limit becomes what? 0. Yeah, you can even think of L'Hopitalling it, honestly, but this would be 250, would go to 0, and this would grow, right? So this is going to go to 0. What do you think is the limiting value or the number of bears that that habitat can support? 350 is the most. So that's kind of, you will not be asked that, but it's good to know. All right, so we just did a weird one. What's next? Trying to think of what one I want you to do next. We'll go take a look at number 1, and then I'm going to give you some Newton's law, and then we'll be done. So on this one, actually I'm going to wait on number 1. We're going to go to Newton's law of cooling. So I'm going to have you switch worksheets. Go to this guy. All right. So for Newton's law of cooling, and I'll go, if you're at home, you're going to just have to watch and write this down on a blank sheet of paper while we do it. But we're going to do a pizza first. But before we do a pizza, I want to show you where it's going. So I'm going to get these guys from the hallway in here. So go to the blank sheet of paper. You guys, why don't you come in, because I'm going to do something new that's not in there. All right. So if you read the scope of this problem, you'll see how cool this stuff can actually get. Now, if Eli is a forensic scientist and he is in charge of figuring out the time of death after a body's been found, and they call him in for his expertise in forensics, right? He will not sit there and do calculus. He'll find some numbers, like he'll say, well, what's the temperature of the room? And they'll look at the thermostat and he'll say, oh, it's 72 degrees, right? And he'll take the temperature of the dead body and he'll write that down. And then he'll wait a while and he'll chart it later. He wants to see how fast the body's cooling, but then he'll plug those numbers into a computer program that somebody else has written. But in that person's computer program, what did they do? Calculus. So this has all been digitized. Technology does all this, but we're going to do it as if we didn't have the technology. Does that make sense? Somebody who knows how to do what we're going to do has already programmed this into a computer program that does it. All right, and all you would have to do, Kelly, is plug in temperature of the room, and then the computer program will say what's the temperature of the body. You plug that in and then chart how many minutes did you wait, 10 minutes, and new temperature, boom, time of death, whatever. But we're going to do it as if we had no computer program to do it. Before we do the dead body, we're going to make it kind of boring. We're going to do a pizza. Right? Nobody would ever take the pizza out of the oven and chart its rate that it was cooling. You just take a bite. If it's too hot, you wait. Right? But we're going to show you how Newton's law of cooling worked. It's called Newton's law of cooling because he's the kind of author of the model. What he discovered is that the rate, hello derivative, of change of temperature, we'll call that capital T. It gets a little, make sure it looks capital to you because we also have as time goes by. So the rate in change of a temperature, and this says Y, but we're going to make it T for temperature, of an object is directly proportional to, and this is where it's different, it's not exponential growth, it's not directly proportional to its temperature. It's directly proportional to its temperature and its difference between it and what we call the surrounding medium. So for that dead bodies problem, the surrounding medium is the hotel room. It'd be the temperature in the hotel room. If I take Carter here over to Lake Orono and push him off the pontoon and he falls into the lake, right? The surrounding medium would be the temperature of the lake water. And his body's going to start to do what? Cool. And it's going to cool rapidly because it's cold out right now and that water's cold. But if I did it in August when the water's like 90 degrees, right? His body will rapidly kind of cool down to 90 degrees, but it won't. It'll go fast and then it'll be done. Does that make sense? The greater the difference, the faster the body cools. That should make sense to you, correct? Put something very, very hot in very, very cold water, right? And it will cool very rapidly, and then it'll eventually approach the temperature of the surrounding medium. And just, you guys are nodding. That should make sense to you, right? So when somebody is killed, I need to know what's the temperature of the hotel room in that next example. And then that body's going to start to cool. It's going to cool rapidly at first, right? So if I get there and I chart and I say, oh, 80 degrees. Ooh, he's cold. He's probably been here a while. Or the room was super cold. That should make sense, right? It makes sense. So what Newton said is that it's directly proportional to the difference between the temperature of the object and what it's in. The greater the difference, the faster we cool. So it says, suppose that for this pizza, the air temperature is 75 degrees. That's your M in the model. So we take the pizza out, we have its change in temperature over time is directly proportional to its temperature minus the surrounding medium. If I take it out and it's burning hot and I take it out in a very cold basement, it is going to cool very rapidly. All right, so now what we do is kind of the same process. I have to chart the temperature of the pizza right now, or the dead body the minute I call Eli in, because he's a forensic scientist, he will take the temperature of the body. The pizza right when I took it out of the oven was 350 degrees. All right, also 5 minutes later, I have to figure out how fast is this cooling, and then I can get a model. I can't use the exponential growth. Do you get why? What part of this model is like, oh, I can't just go T equals CE to the KT, the minus. Yeah, so this has to be done, you know, kind of all the way on out. There is an algorithm for it, but you would never remember. So we're just going to do it in full. So we separate our variables, right? So equals k dt. After we separate, we integrate. We've got this flow down really well. What do I get for the antiderivative on the left? Pure ln. Why does this one not need the negative that my last bear example needed? Yeah, the t. It's u prime over u, and the derivative of t minus 75 with respect to t is just 1. It's not negative. So this is good. This will equal kt plus c, like always. If any of you do this because you've seen me do it, don't. Okay, I do it because I get sloppy. Don't do that, because if there's a point for antiderivatives, this expression is not the antiderivative of that. Do you get that? You wouldn't earn the antiderivative point. So I do it sometimes and I shouldn't. You should actually stop and write e to the ln. Are you okay with that? Now I'm going to do it. I'm going to do exactly what I said for you not to do. If this was an FRQ, though, I just forfeited my antiderivative points. Does that make sense, Alexis? Why? That's not the antiderivative, and I never have it set there. All right, so on the left, I have t minus 75. Perfect. On the right, I have what we always get. We say, well, this is actually times e to the c, and this is just, we do get that sect is kind of in them all, but it isn't all of them. All right, my goal is to write a model for the temperature. So I'm going to say the temperature at any given time is 75, I'll add it on over, plus C e to the kt. What two things do I need to find? Yes, and that's why you get 2 points. The difference is, for the pure sect model, C is the initial condition. For this one, I need to find C using the initial. So it said the oven was set at 350, the pizza came out at 350 degrees, and that has to equal 75 plus C e to the 0, which is 1. So who's C? do a little arithmetic. 275, is that right? I hate arithmetic. So I'm back to my, what we call solution or model. So this would be 75 plus 275 e to the kt. Am I going too fast, guys, or are we good? Now what do I need to find? Okay, that's why I had to chart the rate that the pizza, which will on the next page be the body, is cooling. So I need to go back, and I indent when I'm finding C's and K's, just so I know. I'm just doing scratch work. But the temperature, I lost the stem of the problem. What was the temperature later on? 112 degrees, thank you. How long did it take it to cool to 112? 5 minutes, so 275 e to the 5k. That needs to get solved for k. You guys go do it on your calculator. Again, if you want to just clip them off, if you want to just go minus 75 equals whatever, divided by 275, natural log, divided by, you guys go do the whole thing and I will steal your k. This would imply k is about, and we really should store it, but I'm not going to. I'm going to steal whoever cranks that sucker out. It should be negative because it's cooling. Yep, so what do you have? Negative 0.40117. We do have a backer, super. So negative 0.40117 is my k. All right, so here's my model right here. And I'm going to assume we stored the k even though we didn't. I'll just point, boom. There's my answer. That will give me the temperature of the pizza at any given time. Now, when we put this to the forensics problem, once we have our model for the temperature of the body, right? And we want to know time of death, which means we're going to be figuring out the T. What was the temperature of the body, assuming nobody was ill, at its time of death? 98.6-ish. Yeah, so you're going to get your model doing exactly like the pizza problem, but you're going to say, well, I want to know when they died. And when they died, their body temperature, assuming they didn't have a fever or something, right, was 98.6. So you'll be plugging a 98.6 in here and solving for T. Do you think it will be positive or negative? Negative, because you had to have died before you were found dead. So we have to go back in time, correct? So I'm going to group you guys up and you're going to do the one on the back. If you're at home watching this, the one that's on the back of their paper is this one, and you should try it as well. I'm going to give the answers at the bottom. If you do it right, the person's time of death, assuming there weren't variables that we didn't account for, if you keep things exact, it's 7:26. I think if you round as you go, it's off by a minute or two. So I'll pair you guys up. All right, so if you're watching the video on this one, we ended up getting a C of 20, whoops, sorry, and a K of negative 0.1438. To figure out the time of death, we had to set 98.6 equal to our model and solve for T. I also told them the answer to number 3 is the time of death is 3:44 a.m. So next one that we'll do together is number 2. So go to your packet to number 2. It's a good one, actually, and it's kind of tricky. So there's another Newton's law of cooling with a turkey, but mostly I think we have it all done, this whole packet for the most part. How many have left, Eldridge? Like 3? We shouldn't have many left to do for homework if we're watching. All right, so radioactive decay, the rate at which, so there's your derivative. I'm going to write d something dt, the rate at which a radioactive element decays, and they measure that as the number of nuclei that are changing per unit of time. So I'm going to call this d nuclei dt, that's how they measure radioactive decay, is approximately proportional to. So they're saying this isn't directly, but it's a really close fit. So we'll put an equals. We probably should put a squiggle, but to the amount of nuclei present. So this is the easier kind. You get why? It's directly proportional to the amount present. This can fall out like this. N equals C e to the kt, where c is the amount at the start. And I actually know that. So read the problem. How much was the original amount of radioactivity? Go ahead and read it. I actually know my n sub 0. What is it? 10. Yep, right here. There were 10 grams. So we can replace that with a 10. This is what makes this one a little tricky. So I was able to use this to figure out the n sub 0. The problem is I really want to figure out how long, so I'm going to be looking for this t that'll take that 10 grams to go down to 1 gram. Maybe that's when we can re-enter that zone. By the way, it's still blocked off there. It's too radioactive. If you haven't heard of it, Google it. It's kind of interesting. But I can't solve this right now because I don't know what. K. So it's all about finding that K, and you need another point, and they really didn't give you one. So I want you to kind of just figure out, how am I going to get my other point? Because I need it. I can't get K until I get my other point. Anyone want to help me? Yeah, go ahead, Golden. Yes. Perfect. Yeah, it took 24,360 years for it to get reduced to what? 5. All right? So there's your other point, which means when I go back, sorry, this is really hindering my movement. I'll say, well, 5 equals 10e to the k times 24,360. Now I can find the k. By the way, this reduces to a half, so the fact that they told me it was a half-life, I really didn't even need to know the 10 to 5 ratio, but we'll just go ahead and write that down. I'm going to let you guys find the K and store the K, because I remember from this morning it's incredibly tiny and it goes scientific notation. So you're really going to want to just store it. Because you're my last hour, I actually remember there was a negative and there were 4 zeros, but I don't remember what came after it. So you guys go solve that for K, and I can't come look at yours, Carter, so when you have it on your screen, will you bring it up here and show it to me? So again, you natural log, yeah, it's going to go scientific notation. It's incredibly tiny. What that's telling you in the context of this problem is this radioactivity, what's it called? Plutonium, did they say? What is it? Yes, plutonium doesn't decay very rapidly. It's hanging in the atmosphere for a long time. So that's scientific notation, negative 2.8 e to the negative 5. So I need to move the decimal 5 to the left, which would give me 2843. Again, you should store that because it's such a, that's a lot of digits to write down, right, Riley? So just go ahead and store it in K. All right, so I'm back to my original model. The number of nuclei present is the amount I started with, e to the stored k, t. So now we have this guy stored. I want to know how long it'll take until the radioactivity is reduced to what? 1. So all I do is say, all right, I need to get you to reduce to 1. So again, you need to solve that. Divide by 10. We'll just go like that. Then what? Natural log to get rid of the e. Then what? Divide by your stored K, and if I remember right, it's 80,000 something that I don't remember. Ah, there we go. 80,000 what? Can someone back that? All right, years. So that's all the ones I'll do with you. I think that leaves 3 for you to do on your own. Okay, it's due tomorrow. Oh, by the way, if you're listening to the video because you were gone, in case there's a snow day tomorrow, we have to do a digital day. If you didn't pick it up yesterday, sorry. Whoops. If you didn't pick it up yesterday, I'll put it in the Schoology folder. So I'll just put like a snow day folder in Schoology and you can print it off. All right, have a good one. Bye.